Today I'm presenting to you a tutorial on a finite element analysis of a plate under tension using Ansys Workbench version 17.2. The plate geometry is given here. It's 400 millimeter long, 200 millimeter wide. There's a hole in the middle with the radius of 50 millimeter, and there are uniformly distributed loads on both sides of the plate to the magnitude of 100 kilonewton each. The plate thickness is set at 10 millimeter, and material properties, for that we're using a linear elastic material with Young's modulus of 200 gigapascal, Poisson ratio of 0.3. We're going to look at normal and shear stresses, as well as deformations in both the X and Y planes. In order to do so, we start by simplifying the structural model of the plates using the symmetry of structure. Then we're defining the material properties in Ansys, constructing the geometry, introducing the mesh, and then we're applying the boundary conditions, loads. Finally, we're running the simulation and looking at the results. The use of the symmetry line allows us to eliminate the side of the plate that falls to the left-hand side or lower part and replacing that with a roller boundary condition. This means that deformation in direction perpendicular to the edge is 0, while the plate can freely deform in direction parallel to the edge. The same rule applies to the other face of the plate, where roller boundary condition is enforced. The original force applied to the side of plate is 100 kilonewton, which will be reduced by half due to the fact that the force is now applied to half of the length of that same edge, meaning that a value of F over 2 instead of F will be applied. Let's start by opening up the Ansys 17.2. Here let's start by changing the units to metric ton and millimeter. And among the analysis systems here, let's start with static structural. I'm dragging and dropping it in this project schematic here. Let's rename that to plate and then make sure to save the project. And as mentioned earlier, let's start by defining the material properties. For that, double click on engineering data, and that will open up this window here with the default material set as structural steel. I'm going to modify the properties and in order for them to match the properties we earlier mentioned. Let's change the unit to megapascal, and let's change the Young's modulus to 200 gigapascal or 200,000 megapascal. Poisson ratio is 0.3, so I'm leaving that as default. And I deactivate all the other properties that are not relevant to our example. These are in particular useful when doing dynamic or nonlinear analysis. Okay, let's save the project and close the engineering data tab. So we've defined the material properties, and now we need to construct the geometry of the plate. The plate, as mentioned earlier, is 400 millimeter long and 200 millimeter wide. There's a hole with radius of 50 millimeter in the middle, and the plate thickness is 10 millimeter. Based on the use of symmetry lines, we have reduced that model to a quarter of the plate, and the boundary conditions have been changed to roller. So let's start with constructing this quarter of the plate geometry. For that, I'm going back to the main window of Ansys Workbench, and let's double click on geometry here. This will open up the design modeler interface of Ansys. I'm going to work in the XY plane. So right click there and hit look at. Now let's start by selecting a sketching tab. Let's start by drawing a quarter of the plate in the form of a rectangle, adding the circle in the middle, and then specifying all the dimensions. For that, let's make sure the units are in millimeter. Rectangle is chosen. Start from this corner here, draw a rectangle, then choose the circle, start from the corner, add a circle. Now let's specify the dimensions. For that, I'm going to the Dimension tab, leaving the selection on General, specifying all the dimensions for the plate as well as for the circle. The length of this quarter plate is going to be half of the length, so the radius is going to remain the same, 50, and the width is going to be half of the actual width, 100 millimeters. Let's bring everything back into the view by selecting this Zoom to Fit button. And then let's get rid of all these extra parts by going to Modify and selecting Trim. Now we are left with a quarter of the plate as required. What we need to do next is to go from this 2D sketch to a 3D representation. For that, click the Extrude option, select the sketch under the geometry, and select the depth of extrusion as 10 millimeter, which is the thickness of the plate. Now simply hit Generate. And in 3D view, you can see a quarter of the plate, which is now fully created. Now let's go back to the main window of Ansys Workbench. Let's save the project, and let's continue with the next step. We have already defined the material property. We have already constructed the geometry, and the next step is to introduce the mesh. For that, I'm double-clicking on Model. This will open a new window, which is the mechanical interface of Ansys. And here you can see the geometry is a solid and is already defined based on our previous actions. The coordinate systems, we leave that as default, and the next option is Mesh. Let's make sure the units are in Newton and millimeter, which is the case here. And now under Mesh, here under Sizing, you can select the element size. I'm setting that as 10 millimeter, which is the thickness of the plate. Simply right-click here and hit Generate Mesh. It's going to take a short while. I can change the view to the XY plane, so the created mesh is now more visible. And you can see the average element size based on this ruler here is approximately 10 millimeter. Now that we have entered the material properties and that we have created the mesh and geometry, the next thing to do is to apply the boundary conditions. For that, I'm returning to the mechanical interface. Boundary conditions are specified here in terms of rollers that restrict deformation perpendicular to these edges. In terms of these two axes, the rollers here restrict motion along the x-axis that is perpendicular to this edge here, and the rollers along this face of the plate restrict motion along the y-axis, which is again the axis perpendicular to this edge. So let's start by selecting Static Structural. Under Support, I'm selecting Displacement. And the next thing to do is to select the face on which this boundary condition is to be applied. For that, let's rotate the structure. Go back to 3D view. Let's make sure the face selection is active. Select the face and hit apply. Along that face of the plate, we would like deformation along x-axis to be restricted. That means x component should be 0 and y component should be free to move, while z component, for the sake of stability, has to be set to 0. This is a 2D example, so the components of deformation along z-axis would be 0 for all the points. Let's rename that boundary condition as x equal to 0. And let's repeat the procedure for the other face of the plate. Support, displacement, make sure face selection is active, select the face, hit apply, and this time we would like deformation along y-axis to be 0. So enter 0 here, and also 0 along the component, as before, for the sake of stability. As for the x component, we'll leave it as default to allow free deformation along that direction. Let's rename that to y equal to 0 boundary condition, and let's change the view back to the 3D. The next step is to apply the load. For that, again, under static structural, hit select, hit loads, and select the force. Make sure face selection is active, and select the face on which the tensile force is to be applied. Hit apply, and change the application of force to component-wise. We would like the force to be to a magnitude of F over 2, where F is equal to 100 kilonewton. So we would like the force here to be 50 kilonewton. And that would mean the force along the x-axis to be 50,000 newton. Leave the other components as default. Now we have one last step to do, and that is definition of the outputs that we want from the model. These include stress and deformation values. For that, click on Solution, select Stress, Normal, and let's rename that to Normal Stress along x-axis. Let's make sure the orientation is x, and that will produce all the normal stresses along the x-axis, or sigma xx. Let's duplicate that result, this time for the y component. Change the orientation to y, and also the shear stress along xy axis. Also, we would be interested in deformation that would include total deformation as well as directional deformation along x and y axes. Now we've constructed the geometry, we've introduced the mesh, applied boundary conditions and loads, and specified the outputs. Let's go ahead and solve the model. This is going to take a while, and that will produce the outputs. Here you can see the deformed mesh, and if you click there, choose Show Undeformed Wireframe, you can see the deformation with respect to the undeformed shape of the plate. We have movement, elongation here, and we have compression here. Here you can see various results, normal stress along x-axis. That is maximum at this point here, point of stress concentration. You can also see, for example, deformation along x-axis, which is 0 along this edge where we have specified a particular boundary condition that limits the movement along x direction, and it is maximum where we have the point of application of the tensile force. The accuracy of the solution, of course, depends on the mesh size that we earlier created. I encourage you to investigate the various results here. For example, the maximum stress along x-axis or maximum deformation along x-axis, which is right now 0.07 millimeter, will vary as a result of variation in the mesh size. For that, you could simply reduce that element size or increase it. In other words, use finer or coarser mesh size and investigate how will that influence the stress and deformation results that you can get from this finite element model. For now, I wish to thank you for your attention, and I encourage you to follow our future tutorials on the use of Ansys Workbench in addressing structural analysis problems. Thank you.